I'm really excited to present the results of a long-term effort, 35 years, which is almost as old as I am, of putting together radio observations of type 1a supernovae. And this just came out a few months ago. So, why did it take us 35 years? I'm going to try to tell you that the dog ate my homework, but that's not the truth. It actually took us to do a lot of homework and put together all the facts and all the figures and put together the right team. And a lot of this was inspired by Roger Chevalier, Klaus Franzen, and Wei-Dong Li, who are not here today, I believe. So these are the people that contributed to the effort here at CFA during this long-term project. Especially I want to emphasize Laura Chomuk and Atish Kamble, Jared Parent, Ryan Foley, Rafaela Margutti, Jay Strader, and Sayan Chakrabarti. So the idea was, why do we care about type 1a supernovae in the radio? Why do we care about non-thermal emission from supernovae 1a in general? And the point is that quantity is not quality. That's not to say that Sloan hasn't done a fantastic job at finding lots of supernovae. They've done a great job. But what do you do next if you want to find out about the progenitors? So what we did is we put together a catalog of 85 radio observations of type 1a supernovae. And it's the most comprehensive radio study of type 1a supernovae to date. And I emphasize young in the sense that a lot of the observations are actually less than 1 year old, and they were taken with the JVLA, which is a factor of 10 better in sensitivity than the old VLA. So why do we want to do this? What motivated us? We wanted to understand, obviously, like we all do, what single versus double degenerate progenitor systems, and how can we diagnose them? Radio observations can be the clue because they can sniff out the environment, whether it's a R to the -2 profile or whether it's a constant density profile, can tell you something about, maybe it maps into a wind versus ISM, a double degenerate, single degenerate system. We also cared about shock physics, obviously. If we actually detected one, that would be exciting. Feedback, we want to understand white dwarfs, dust formation, destruction, binary evolution, and also, of course, supernova homogeneity. That became an underlying theme towards the end of the project. There was also a great time to do this because it was new optical time domain studies, including PanSTARRS, PTF, CRTS, LSST, Assassin now. And we have great strides in improvements in amateur facilities and the communication with them. And of course, new long wavelength facilities didn't hurt. We also want to build a better connection between supernova community and the nova community and the supernova remnant community, which our chair will, I'm sure, appreciate, because they're all connected and we should have more of an inclusive community to discuss this progenitor issue. So, all right, a supernova, right, hallmark is a big pimple on a galaxy, essentially. The bolometric luminosity peaks in the optical, 10 to the 42 erg per second. That's a thermal emission signal, which we've heard a lot about. Underneath it, there is that non-thermal signal, that synchrotron emission that is coming just from the blast wave plowing out through the interstellar medium. The time scale is a few months for the optical, so you only have a short window in order to discover the supernova. And it's just fantastic that the decay time scale of nickel 56 happens to balance out the diffusion time scale, so that's fortuitous. But what we try to do is to also observe the supernovae in the other bands, the radio, the millimeter, and the X-rays. In the X-rays, you can get an extra component, which is the inverse Compton upscattering of the emission coming from the innermost material, which I'll discuss in a second. Okay, so this is a cartoon version of a supernova. Basically, there's a forward shock that's plowing out, and it's shock accelerating electrons to relativistic speeds. A reverse shock is going backwards and shock heating the inner material. Then there's the optical photosphere, which is sort of like the heart of the explosion, and that's what we use to type all supernovae, even though there's a lot more information on the outsides. The energy, kinetic energy, is coupled to the velocity with a power of -5. So there's very little material in the forward shock. It's traveling very fast. It's a homologous explosion, but it tells you something about the explosion. Plus, you can observe in the radio during the day, and that's that's better. So how do we do it? We cherry pick. We don't observe every supernova. We're not going after quantity. We're going after quality. So we pick the ones that are optically discovered. Look, there's a pimple. And then the supernova campaigns find these objects, and they fortunately publicly announce them. And then we pick a few to study as part of our long-term radio study. So this is our old-fashioned picture of a type 1a I remember this from when I was 19, type 1a supernova. And one of the things that we had to do as part of our homework was to actually identify different flavors of type 1a supernovae. And that's been happening in the whole community. And I am going to credit Jared Parent and Ryan Foley to make this happen. We now know there's 1AXs. There's low luminosity supernovae. Those are the 91 BGs. There's 91 Ts also. There's calcium-rich supernovae. There's cool and faint type 1a supernovae. There's broad-line supernovae, shallow silicon line supernovae, superchandrasekhar supernovae, and supernovae that are interacting with a medium. So there is actually H-alpha emission in the spectrum. And we tried to put all of this together for all of the radio observations that have ever been taken for type 1a supernovae so we could understand why we don't see any radio emission. There's got to be something out there, right? And so we compiled this as part of the paper, just so that we all had our brains together. And I'd love to tell you that we detected something, but we didn't. I'll tell you why that's actually important at the end. There's no detections. So this is a plot of the 5 gigahertz, and I picked 5 gigahertz because that's the most sensitive band you can use with the JVLA, the improved VLA, versus time since explosion. The first curve here is a wind curve, so it has an r to the minus 2 profile. It goes up and down, basically, is all you have to remember. And the bottom one is a constant density profile. What's interesting about type 1As is that you can distinguish between the two progenitor scenarios using the radio. So if it actually goes up as a function of time, you can figure out which one is which. Unfortunately, we did not detect any of them. But you can tell that we actually did our homework and looked at a number of them. You'll recognize a number of these zip codes. They're probably some of your favorite events, like 14J and 12CG and 11FE. All of these were part of the campaign that we really worked hard. I should also say that we have assumed that the amount of energy that is being put into the electrons and the magnetic fields is equal, and it's about 0.1. And just to give you an idea of why that is an impressive plot is that this is what it looks like when you actually detect a radio supernova. They have curves that go up and down. That's a wind scenario. That's a core collapse supernova. This is a nice compilation of type 2b supernovae put together by Jason Dittman, a student at Harvard that I'm working with. And the bottom of the plot is where all of those upper limits would lie for the type 1As. So it's an incredibly distinguishing feature. You can actually use this information to say, is it a type 1A or is it not? We detect about 15% of all type 1BC and type 2 supernovae within 100 megaparsec. Within 30 megaparsec, we detect almost 100% now with the JVLA. So that is a very important thing to take away, that you can actually use radio instead of just a spectrum to figure out what kind of object you're looking at. And I think this will probably be underscored also by the interesting events that we've been finding, that you can't tell if they're actually a weird 1BC or a weird 1A. They're hydrogen poor. That's all we know. All right, so bottom line, just to hammer it home. Young supernova 1A, and when I say young, it's less than 1 year old. Young supernova 1A do not show detectable radio emission. And that's just the bottom line. We have tried our darndest. These are just the different models we put together to see how constraining they are versus like a r to the minus 2 versus an r to the just a flat density profile. There's just nothing there, it seems like. And so what are the actual limits? Well, we have another way of going about this, and I'm sure Rafaela can expand on this. This is nice work that she did on 14J. Young supernovae 1A also don't show X-ray emission, and that could be either synchrotron or inverse Compton photons. There's nothing there either. So we give the same limits in both cases. It's a mass loss rate that's less than 10 to the minus 9 solar masses per year. So put together a scenario where you can actually accrete material and not show any evidence for detritus afterwards. There's no napkins left over. So they eat clean is basically our conclusion. All of these progenitors for type 1A supernovae are eating very cleanly. There's nothing left because the radio should show it. And our best scenario, our best situation is that less than 10% of supernova 1A are in single degenerate red giant systems because there's no way that they could eat so cleanly and not leave something behind. And that's a pretty strong limit that we're going to have to battle with. And that is for, I should say, a wind velocity of 100 kilometers per second. You can mess with that. You can mess with that parameter and also those epsilons. But it only gets worse. So in the future, I think that the spectral diagnostics are going to be increasingly more important. I think that that's the lesson that I learned, at least, for going through this whole process. And I think Jared Parent has done a great job with Danny in putting together this whole sort of recipe for how we do that. And looking forward towards the future, I think also looking backwards is important. So work with Sayan Chakrabarty was instrumental in showing us that looking at the remnants can actually be important too, because you can actually see evidence for the supernovae in constant density profile increasing in their radioluminosity as a function of time. And we didn't see it in the case of G1.9, which is 110 years old. So the next one is going to be 1885A. I think we should all keep our eye on that one. Of course, if there's the next galactic supernova, we'll all keep our eye on that one too. So definitely study the new ones. Let's definitely still keep doing our target of opportunity studies and plugging away at the optical spectra, but let's not forget our old friends. And I think the last thing I wanted to just underscore is that we need a multi-wavelength supernova catalog. And so that's something we've started doing, and I applaud the James and Jared for starting this. And the first target in our in this study, this is what it looks like. I think that it's been mentioned before. The first one will be 11FE, which actually has all the radio and X-ray data there, and it's open to everybody. You can upload anything you want, and it'll have all the radio and X-ray for not just the 85 type 1A supernovae, but for the 256 type 1 BC supernovae that I studied as part of my thesis. It'll have everything we've collected so far, and all of the hard work that, of course, Rafaela Margutti and others have done. So I would definitely look forward to that.
So in the single degenerate model, we have to take into account the rotation of the white dwarf.
Yep.
And rotating white dwarf has a somewhat higher Chandrasekhar mass compared with non-rotating. So we modeled the time delay between the stop of accretion until the carbon ignition during the the breaking of the rotation of the white dwarf. So after the 100 million years or so, then the white dwarf explode. So the companion star already become a helium white dwarf during that time. So, and also the circumstellar material could be disappeared. That's, I think, a good possibility.
I completely agree. That's why I think that we need to look forward and we need to look backward. We need to look at the novae and we need to look at the supernova remnants, and if we put all the information together, we might get somewhere. That mass has to be out there somewhere. That's all I think.
Anyway, the indication of the helium white dwarf companion would be interesting.
How soon would you have seen something, and what would it have looked like?
It would look just like this. This is a perfect example of what a supernova looks like when it runs into the material that it polluted its environment with before it died. It should look something like that. And we've tried so hard, and there's just nothing there, which is interesting. I mean, it's not a failure. At first, I thought it was a failure, but it's not a failure. We tried.
Alicia, taking from that question, so no detections.
No
right?
detections.
But you mentioned amongst the various zoo of type 1A classifications, the 1A CSM, which apparently is interacting with something,
I know.
but no radio detections on those.
It's actually easy to hide the radio emission or the X-ray emission if you put it out far enough. So if you put it out of a parsec, it can be easier to hide, is I think the solution we came up to. But I'm looking for like clues from the audience here. There was a panel discussion next, so we don't know why.
Because the spectral signature give the indication that the supernova
There's
is actually
hydrogen in it.
interacting
I know.
with something, but you're saying a distance.
It has to be far enough away that it's basically not a Stromgren sphere. I don't know
Okay,
anymore. I don't know.
yeah. It may be.
Type 2N supernovae make radio emission. Type 1A CSM don't. So there's something different.
Right. In the type 2 case, it can be actually prolonged because it can be optically
Exactly.
thick in time, right? So perhaps ongoing monitoring would help in this situation.
We've
right?
tried. Oh, but yeah, that's a separate conversation.
In the back, yeah, Dan.
Just to follow up on that, I mean, type 1A ceases are very rare and tend to be found far away, so I don't know how your limits compare in luminosity compared to the typical type 2s. Would you have seen that level of emission in the type 1A
Okay,
CSMs that
again,
you
so
have?
this is what a typical core collapse supernova looks like. These are even wimpy ones. These aren't even like the grown-up guys. So the type 1A supernovae are way down there at 10 to the 25.
Yes, I mean, the normal ones are, but the type 1A CSMs are rare and found much further typically. So I was wondering where those specifically fall on your plot.
Oh, so, I mean, they are rare. So O2IC and O6GY, we went after them like crazy. Nothing. And the factor of 10 increase in sensitivity with the JVLA should have popped them up, and we've monitored them for 10 years. I don't know where, I think it's just pushed out far enough, and the material is distributed in such a way that the forward shock is not able to create a detectable signal, is all I can think of. But as I said, again, I'm open to suggestions.
Complete speculation from a complete outsider, but so if you have a double degenerate, then it's very low luminosity, and any mass that went out recombined, very likely, and when it recombines, it loses its magnetic field. And I don't know what the shock will do. The epsilon sub b is, of course, basically guesswork.
They could change,
Yeah,
exactly.
but it's conceivable that the magnetic field is much less in the outflow from a dim object than from the outflow from a supergiant, especially perhaps a massive supergiant that's, especially a hot supergiant that will keep matter ionized.
I think so. All of the modeling is based on type 1 BC supernovae. So these are naked, we call them naked supernovae because they have no envelope. And I don't think the shock physics should be so different. And we typically see epsilons that aren't so out of equipartition. I mean, they're just simple arguments for shock physics. The brightness temperature has to be, well, I'm not lecturing today, so, but I don't think it could be that much out of line. So I don't know. Epsilons could be changing for white dwarfs, I guess, is what could be the solution. I don't know. I'm sure you can turn lots of knobs, and we could turn it all down. But I'm just saying, as an observer, it is anomalous that we don't detect any of them. None of them. Nothing.